The enthalpy of vaporization, also known as the heat of vaporization or heat of evaporation, is the enthalpy change required to transform a given quantity of a substance from a liquid into a gas at a given pressure. It is often measured at the normal boiling point of a substance, although tabulated values are usually corrected to 298 K. The correction is often smaller than the uncertainty in the measured value. The heat of vaporization is temperature dependent, though a constant heat of vaporization can be assumed for small temperature ranges, and for reduced temperature, the heat of vaporization diminishes with increasing temperature and it vanishes completely at the critical temperature, although kilojoule per kilogram or J per gram, and older units like kilocalorie per mole, cal per gram and BTU pound are sometimes still used, among others. Physical model for vaporization. A simple physical model for the liquid-gas phase transformation was proposed in 2009 by Joseph Garai. It is suggested that the energy required to free an atom from the liquid is equivalent to the energy needed to overcome the surface resistance of the liquid. The model allows calculating the latent heat by multiplying the maximum surface area covering an atom with the surface tension and the number of atoms in the liquid. The calculated latent heat of vaporization values for the investigated 45 elements agrees well with experiments. Another model which utilizes the data set from Joseph Garai's model shows that the liquid-gas phase change can be explained in terms of kinetic theory by considering that the energy required for vaporization is extracted from all 6 of the vaporizing molecule's neighbors. This includes or required rethink of the probability of vaporization, and has consequences to the Clausius-Clapeyron equation. Moreover, it does resolve the issue of the latent heat of vaporization being significantly greater than the thermal energy exchanged between molecules, i.e., at boiling point the latent heat for water is approximately 13.2 times kT enthalpy of condensation. The enthalpy of condensation is by definition equal to the enthalpy of vaporization with the opposite sign. Enthalpy changes of vaporization are always positive, whereas enthalpy changes of condensation are always negative. Thermodynamic background. The enthalpy of vaporization can be written as it is equal to the increased internal energy of the vapor phase compared with the liquid phase, plus the work done against ambient pressure. The increase in the internal energy can be viewed as the energy required to overcome the intermolecular interactions in the liquid. Hence helium has a particularly low enthalpy of vaporization, 0.0845 kilojoules per mole, as the van der Waals forces between helium atoms are particularly weak. On the other hand, the molecules in liquid water are held together by relatively strong hydrogen bonds, and its enthalpy of vaporization, 40.65 kilojoules per mole, is more than 5 times the energy required to heat the same quantity of water from 0 degrees Celsius to 100 degrees Celsius. Care must be taken, however, when using enthalpies of vaporization to measure the strength of intermolecular forces, as these forces may persist to an extent in the gas phase, and so the calculated value of the bond strength will be too low. This is particularly true of metals, which often form covalently bonded molecules in the gas phase. In these cases, the enthalpy of atomization must be used to obtain a true value of the bond energy. An alternative description is to view the enthalpy of condensation as the heat which must be released to the surroundings to compensate for the drop in entropy when a gas condenses to a liquid. As the liquid and gas are in equilibrium at the boiling point, delta Vg equals 0, which leads to, as neither entropy nor enthalpy vary greatly with temperature, it is normal to use the tabulated standard values without any correction for the difference in temperature from 298 K. A correction must be made if the pressure is different from 100 kilopascals, as the entropy of a gas is proportional to its pressure. The entropies of liquids vary little with pressure, as the compressibility of a liquid is small. These two definitions are equivalent. The boiling point is the temperature at which the increased entropy of the gas phase overcomes the intermolecular forces. As a given quantity of matter always has a higher entropy in the gas phase than in a condensed phase, and from the Gibbs free energy change falls with increasing temperature. Gases are favored at higher temperatures, as is observed in practice. Vaporization enthalpy of electrolyte solutions. Estimation of the enthalpy of vaporization of electrolyte solutions can be simply carried out using equations based on the chemical thermodynamic models, such as Pitzer model or TCPC model. Selected values. Elements. Other common substances. Enthalpies of vaporization of common substances, measured at their respective standard boiling points.